So people throughout the ages have always known the importance of tactile sensing, even back in the arts and sciences, as evidenced by this picture, the sense of touch. Tactile sensing is a much more difficult and interesting problem than a lot of the machine vision issues. So you've seen probably the Xbox Kinect, very fancy, but you've noticed that a lot of the touch-based devices are much more limited. You probably get a vibrating cell phone or other haptic buzzers in your controllers, and that's about it. Well, one of the reasons is because the feedback from the touch receptors of any robotic or prosthetic finger are highly dependent on the robot or hand that makes those motions. A good example of that is if you take your hand and put it on your shirt. If you just touch it, you don't get a lot of information, but if you start moving your fingers around, then you're able to tell, oh, all right, this is soft or smooth, or other information about the fabric. So one of the strategies that we've decided to take is Mother Nature has devoted a lot of time to figuring out what the relevant signals are in these things. So why don't we try to emulate those in artificial sensors and see what we can do with them. So besides from advancing the plot of iRobot, I think one of the points is that if we're going to have robots assisting, using human tools, doing the same type of tasks that humans do, it's useful to examine human type of strategies. So we come back to biomimetic tactile sensing. And again, this talk, I'll try to glean over the, just cover the technical parts quickly and get more of to what we'll be doing and those type of things. So there's two types of touch, cutaneous touch and proprioceptive. Proprioceptive is your joints. I shut my arm, but I know where my hand is in space. Well, that's because of the proprioceptive receptors. We're focusing on these guys. So force and deformation, thermal sensors, and the microvibrations in your sensors that are in your fingertip. And the goal is to, of course, figure out what makes those and how do we replace those with an artificial sensor, which we've done here, called the BioTac. So one of the things that I want to convey is touch is not a touch-based camera. I'm not taking a picture of the surface, if you will, with a touch array. It's this estimation of vibrations and forces and thermal sensations to give me a qualitative and quantitative estimation of is the surface rough, smooth, hot, cold, that type of thing. Just cover this really quickly. I'll show more in the demo, but we have 3 sensing modalities: micro vibrations for texture and slip, forces, and thermal. Okay, and then one of the things that's important is that it's not just great to have one of these separate sensors. So if you go online, you Google and try to buy a sensor, you'll often find that you'll have one sensor that picks up one type of thing: pressure, airspeed, whatever. Here we emphasize it's important to have all 3 modalities working together. And again, I come back to the lapel argument. If I touch my shirt and move my fingers back and forth, how hard and how fast I move those affects my perception of the object. Here's one of the applications. This is something that we're doing at Syntouch. So what you're seeing is a prosthetic hand going like that and adjusting its grasp to a styrofoam cup. So often in industrial robots, if your robot has to grab something, it just grabs it and grabs with all its might and moves it from A to B, and you prevent it from dropping it that way. Can't do that here. So finally, what are we actually doing at Syntouch with all this research? We're working on a Barrett robot kit. Barrett is an industrial robotics hand that's available, made by Barrett Robot Company. So I'll show you a little bit more of that later. But the 2 primary projects we have are a prosthetic hand augmentation system. Basically, we're working on the next generation prosthesis. That's an effort funded by the National Institutes of Health. So that's working on integrating the hand with prostheses, but also how do you get that data back to people. And that's mostly communicating with the stump. So that would be a really good, very hands-on project for folks to use. You can put on the different tactors that convey this information to you: slip, temperature, vibrations, whatnot. The grant that I'm the PI on is the Shadow Hand and Robot. It's a fully articulated, looks like a black Terminator hand. This is a very expensive, about a $400,000 system. The idea behind this grant, which is funded by the Department of Defense, is to autonomously identify objects. So basically you hook this guy up to a computer, reaches around, tells you different things about the object, what kind of shape, what's it made out of, is it compliant, hard, soft, smooth, sticky, that type of thing. I talked about the Barrett hand, so what exactly are we doing this thing?
Barrett robotic hand, wrist and arm module.
So this is Jerry Loeb, who's at USC. So if you want to see this system, I'm sure he'd be amenable to working with some guys here at USC as well.
Much better function in dealing with objects whose mechanical properties are unexpected.
Yeah, you can't see it. It's probably going to be over before we...
In which the grip force must be controlled to maintain grip without damaging.
Okay, so we got a robot grabbing a cup and a robot grabbing a tomato. So you would think robot might squash tomato. No, it doesn't. All right. Okay, so one of the things I can do if we have time, I can show you a quick demonstration. Just to prove I'm not blowing smoke here. Okay, so this is just different outputs of the device. This is the first derivative of temperature, that's the first derivative of pressure, and that is the essentially a 2D splayed out version of the force array. So here's what the device looks like with the cable coming out. So as you can see, I push down. These are scaled to the color, so they change. And AC pressure is pretty sensitive. So it picks up very, very, very light vibrations and transients. And if I put this, you'll see this kind of, see this thing is about the same temperature as my finger, so it doesn't change too much, but if I were to put this on an ice cube or something, you'd see it, there we go, a little bit of a change. And then when I let my finger off, it heats back up. So I'll just kind of let this run. I suppose it's not too feasible to have everybody come up and check it out, but I'd be happy to answer any questions.
I have a question.
Yes?
Like when the arm was picking up the cup and then the tomato.
Yep.
Does it know ahead of time? I mean,
where it is and that sort of stuff?
What do you program it? Okay, now you're going to get a tomato, so apply less pressure.
No, that's the whole thing, is that you use basic vision. That was using it was open loop, I'll be honest, but our whole goal is to use really cheap vision, like a Microsoft Kinect, to gather, oh, it's right about here, and then you kind of fumble around, and then you use the touch sensing to do the more elegant handling of the object. That's why, is this your bag?
Yes.
Okay. So when I pick this up, I'm not doing this the entire time watching it, so you hold on to it and you kind of forget about it. That's because the tough part is grabbing onto it, and then basically your touch sensors take over once you're...
So somehow ahead of time it knows maybe some information of what type of object is in front of it, right?
Yeah, and that's one of the things that we're doing with the DARPA grant is kind of building up a priori information. So you gather, based on vision and eventually touch, you have an idea about what to expect, and then it updates those properties. It essentially learns.